Well then, welcome to the last segment of today's consortium. And I'm Andreas Schwab from Iowa State University. I will introduce you or try to introduce you to Bayesian Statistics and Bayesian Analysis. So in a sense, I can quote Monty Python here, now on to something completely different. And in the process, you should recognize that Bayesian is a complex, well-established methodology. And in that sense, we have to be realistic, or I have to be realistic with regard to what can be accomplished in a 20-minute presentation. So you will not leave this presentation being an expert in Bayesian. Instead, my bar that I've set for myself is much lower. I hope that I will be able to plant a seed in your mind that there is something potentially interesting called Bayesian analysis, that I increase your awareness, and that from here on you might see papers and pay more attention to it and accumulate knowledge over time. And maybe I can entice you to take Bayesian statistics serious and at least consider maybe experimenting with it in some of your own work. So again, my point is I'm going to introduce you to Bayesian on a very fundamental level, but Bayesian is a very complex approach that has a lot of choices to make. And making these choices and learning about them really takes time and effort. So I would also like to start here. There we go. Give you a little bit of the journey, because it was mentioned earlier that this is a clan, and how did I join the clan might be of interest, because that is also part of how we progress through the profession. And we often have this idea that the actions we take are pre-planned, proactive search and other logical approaches driven. I have to admit, in my academic career, a lot of things have happened accidentally. And my exposure to Bayesian was also accidentally. And my encouragement, especially after a talk like Asli's talk about taking theory serious with regard to guiding you, I think I would second that with another thought, but take puzzles that you run into seriously too. Even if they don't fit any theory or seem to be not fitting, they can be pointing into directions that we just have not explored, while the theories are strongly driven by what we already know. So having said that, how did I get into Bayesian? I did not find Bayesian statistics. Bayesian statistics found me. And here's how that happened. I've been doing for many years now, it's close to 15, close to 20 years, workshops at the Academy of Management with Bill Starbuck, Eric Abramson, and a variety of other individuals on the challenges and limitations of statistical significance tests, including segments on what we should do alternatively. And we've been doing this 2011, around about 5 years. And out of the blue, we received a telephone call from David Krekart, who was on the phone completely excited about Bayesian statistics and wanted to convince Bill and me that we definitely have to add a segment with Bayesian statistics to our workshop. And I don't know if you've seen presentations by David Krekart, but if he gets excited, and he can get excited about method things, he gets really excited. And he gets really convincing. And that was my exposure, which is kind of surprising, and was surprising to me, because I had been trained at the University of Wisconsin with a heavy method focus. And I had went through the full curriculum. And the term Bayesian did not occur a single time. That was in the 90s. I'm sure the world has already changed a little bit. And some of you will have had exposure already. There is a lot more stats departments that are paying closer attention to Bayesian now. But in general, I was completely flabbergasted that there would be such an exciting or potentially exciting methodology out there that I hadn't even heard about. So in that actually led, we fought David off because our long workshop did not allow us to integrate another segment of that length, but we collaborated with him and started giving symposia and workshops just on Bayesian statistics. And that is how I got roped in and eventually convinced that Bayesian is actually a very helpful tool for us. I would even go so far, it's a helpful tool even if you want to stay a frequentist. Bayesian tells you a lot of what frequentists can tell you and cannot tell you, and thereby can make you a smarter researcher with regard to exploiting frequentist approaches. So having said that, let's delve into Bayesian analysis. So Bayesian statistics offers an established methodology for drawing inferences and assessing the plausibility of theories. It's the same thing that we kind of expect from frequency statistics, but it does it in a different way, and it has, in my opinion, some advantages. So what does it provide us? It provides us probability statements for hypothesized effects based on the specific observed data. The difference of the p-value that Brent already mentioned is that it is a probability statement of observing this data, making assumptions about the population. And in null hypothesis testing, the assumption is that there is no effect in the population. So you're doing a probability evaluation of a hypothetical population that you created, one of no effect, and then making probability statements about how likely is it to actually see that data. So here, Bayesian statistics is making a probability statement about, is the hypothesis true? Is there an effect? And that's a substantial difference, completely different meaning. Then Bayesian statistics is, in a way, strange because it does require you that you actually specify a prior. You have to make a statement about what effect you're expecting in the population, and it uses that effect that you're expecting in the calculation of that probability. And we'll get more to that, but specifying prior is something people are not familiar with, and thereby that creates challenges for it. I will try to convince you that it actually is not a challenge, it's actually or simultaneously an opportunity. It is actually a benefit of Bayesian statistics if used correctly. And then Bayesian is less about making dichotomous judgments about, is there an effect, is there no effect, do we have something? So it is more about seeing distributions of effects and then comparing this to hypothetical distributions that we see or across models. So it's a lot more detailed, nuanced evaluations of what we're seeing in the data, while frequentist and p-value driven evaluations are dichotomized into either effect or no effect. And that actually throws a lot of information away that might be valuable to kind of incorporate into our evaluation of theories and make it part of the theories. So that's the three things, key elements in what Bayesian can provide and that can be helpful. So as I said, different approach. So thereby we have to leave our frequentist statistics behind, and we have to recognize that this Bayesian approach fundamentally works through three steps that we have to make. And I will lay out these steps so you get a sense of how Bayesian statistics works. And these three steps are that you first have to specify a prior distribution. The second step is that you estimate the posterior distribution using the collected data. And then you evaluate and interpret the posterior distribution. Let's talk about each of these three steps in turn. Let's start with the specifying a prior distribution. Now, specifying a prior probability distribution for the parameter based on some prior knowledge and assumptions about the parameters. So we have to draw on what we already know. Now, there may be situations where we really claim we have no idea, absolutely none. And for those situations, Bayesian is not invalidated in itself. It has an option for that to kind of use that in your modeling. And that is what we call uninformed priors. So uninformed priors usually assume that if you have categorical data, that each of the categories is equally likely. Flat, we often call that flat distributions. If it's a continuous, you would read, again, a flat distribution or a normal distribution with extremely long tails and again, flat. But in most cases in our research, we've been studying these things for years and years, for decades. So we're not completely naive about them. And in most cases, we actually do have knowledge of what we expect. And in that sense, Bayesian has the advantage through the priors to allow us to incorporate what we already know into the estimation of what we think we can learn from the data. So in that sense, Bayesian doesn't always start from scratch again. We could always do uninformed prior again and run that. But it kind of says like all the 20 studies before have found no information that could help me to make my estimate better. Okay. If we do that, then informed prior studies would be the alternative. So if you study mergers and acquisitions, I have later a merger and acquisitions example, there may be a meta-analysis. That meta-analysis may say what the average effect is. Well, now I have an objective average effect that I can use to kind of center my distribution. They'll have dispersion information, and you can use that to kind of say, this is what the distribution should look like. And thereby you have a prior that is not subjective, but based on what prior research has been showing. And that will help to make my eventual estimates more precise, assuming the prior research was accurate. Okay. If I have, again, the assumption all this prior research is complete garbage, then of course we're back to uninformed priors. But if I think there is some value, then even these rough estimates will make my eventual posterior distribution more accurate versus just assuming completely flat, no knowledge. Alternative, Asli was pointing correctly to theories. We have lots of theories. I think actually we have too many theories. And thereby there's a lot of sources with regard to making judgments and prior distributions based on that. Sometimes different theories might tell you different things that would allow you to run your same analysis with different priors, or combine different theories to develop an overarching prior. All these are actually, I also think, good exercises. If you're a doctoral student, for example, thinking about your dissertation, thinking of this goes close to what Asli was telling about. Think carefully about your phenomenon, think carefully of what we already know, and don't necessarily get hooked just on one source to do that or one theory to do that. There's another source that other fields have been using aggressively to define priors and not have the researchers be the primary source of determining the prior, and that is asking experts or practitioners. And that seems to be something that in our field is especially relevant, as we are typically studying things that managers make decisions about. And thereby we could ask them of mergers and acquisition, what do you think the average benefit of it is? What value do you expect? What do you see the risks around it? And we could use that as a starting point, which might be better than just assuming we know nothing. The last point here is results from prior stages of data gathering. And that actually becomes increasingly important as we're entering into times of big data. Companies are increasingly collecting all kinds of information on an ongoing basis. We can scrape internet sites regularly, and thereby we're entering a stage where we might run some new model on the latest data we have collected, but we might use as a starting point the data from last month. And you will actually see a lot of some of the AI, the artificial intelligence, some of the learning mechanisms there are using Bayesian logics, which is an updating logic based on prior data. So yes, priors specifying is something very unfamiliar to management scholars who haven't been exposed to Bayesian. But I think I was able to convince you that this is not magic. This is something that can be done systematically, and that can be done transparently, and that can be justified to reviewers. Also, there's one other element, and that goes a little bit into the robustness question we just had. In Bayesian statistics with priors, there's always one easy way to kind of address questions you receive from reviewers with regard to what if I use this prior? Well, you can run it with that prior, and you can see if it makes a difference or not. And that's my last bullet point. Sample size plays quite a role with regard to the influence of priors, which means if you have a large enough data set, priors just don't matter anymore. Your results will be driven by the data. And then the entire discussion of priors becomes to some degree mute. And how large of a data? Well, that's a more difficult question because it depends a lot of the nature of your data. It depends on what priors would make sense. It also depends on the complexity of the interdependence within your models. But larger data sets, I guarantee you, if you get 1 million observations, you're pretty safe on the side that priors will probably not make an effect. The other element with regard to priors is that if you see it as a challenge, it can also be an opportunity. Where's the opportunity? The opportunity is that we're currently limited with regard to sample sizes. Smaller samples just don't get studied because we don't find statistically significant effects. And but sometimes we have rare events that still deserve studying. And then we get into Asli's part, we can do descriptive things with them, but statistical significance because of the noise in the data will not work. Bayesian statistics has been used in other fields exactly in these situations. So I used to have a colleague here at Iowa State in the stats department who did Bayesian analysis before for NASA. And at NASA, they had sometimes very limited space experiments on something, and they still needed to make judgments with regard to what's the probability that something would go wrong or go different. And they can do better guesses out of a sample of 5, than just assuming we have no clue what's going on. And I think if you talk to managers, they will second that notion that currently we're studying things that are very observable, but there's a lot of stuff that would be of high interest to managers where even rough guidance would be helpful, but we're not engaging in it because our methodology currently blocks us with regard to investigating that. Bayesian might be an opportunity to do some of that. And then the last, that might sound a little weird, this unaccounted heterogeneity issue is, again, we're studying currently very large samples, sometimes out of necessity, because otherwise we're not finding statistically significant effects. But these samples are often highly heterogeneous and high risk of spurious relationships. If we find a methodology that allows us doing reasonable tests at smaller sample sizes, we can create more homogeneous studies. So studying mergers and acquisitions for Fortune 500 companies is incredibly heterogeneous. But if I study this in an industry with 50, I might need a different tool with regard to making reasonable judgments about that. And that's an opportunity. And in that, let me also say, I don't see necessarily frequentist approaches or qualitative approaches or Bayesian statistics as either or. You have to be in this religion or in that religion. I think these can all inform each other. And there is a value of running large samples of heterogeneous nature to test for effects, but there is also a value with regard to doing focused studies on more homogeneous subsamples, and they can inform each other. Good, so that was on priors. Let's now get to what's often called the Bayesian magic, which is how do we actually make judgments? So what Bayesian analysis produces is called a posterior distribution, and that's the distribution of the predicted effect, both in size and uncertainty. But how do we get that posterior? The posterior is estimated by updating the expected distribution, that's our prior, by using the observed data. And that updating is done using Markov chain Monte Carlo simulation. And that is the Bayesian magic. And it's correctly called magic because before the advent of the computing power we have today, that was the main reason why Bayesian analyses were not used. Because when you had to do this through calculus, there were all kinds of restrictions and limitations. Now, I think nearly any Bayesian that I know is running the simulation approach with regard to finding solutions. And this is complex. So just to say, what does the Markov chain do? In the end, we're doing multidimensional integral optimization. So the integral for the entire space that you have on all the dimensions that you included in the model gets optimized. And that requires substantial computing power. In the end, that leads to this posterior distribution that then can be interpreted. And I think I'm going to make the argument that there's a lot of very valuable information in these posterior distributions. And the information that's in there should be the prime motivation for running Bayesian analysis. So what does the posterior distribution show? I just have a chart that you'll see again in the example in a second, but it is a graph that shows the effect that was hypothesized and the likelihood of the effect at different sizes to be occurring. And our null hypothesis would in this case be the zero effect, no effect, and then you have effects to the right and effects to the left. That allows you very flexible probability statements. We'll see in a second. This also allows you to calculate these curves for alternative models based on alternative theories, based on alternative data sets, and you can overlay them and see how they're different and can see very differences in patterns that tell you a lot about what's happening in your data, potentially can tell you a lot of what's happening in your data. A lot more than just a dichotomized judgment of there is an effect, right? Good, so that was abstract with a lot of terminology, but I think I want to walk you very quickly through an example to just illustrate how that really pans out. And I'm going to use an example here. This is not the greatest Bayesian study ever done, but just one of the early ones, and just an illustration of how it can be done. So again, Bayesian is very flexible and needs flexible approaches. So don't read into one example that we should apply exactly the same procedure to the next. That requires more thinking and adjustment. Okay. This is the Hansen-Perry-Rees study on Bayesian operationalization of, again, the resource-based view, old publication in Strategic Management Journal. Their fundamental objective was they wanted to see the effect of administrative decisions on firm performance. And they had multiple hypotheses about different decisions that top managers make. We're going to focus just on one. We're going to focus on the decision of buying an organizational unit improves firm performance, so mergers and acquisitions. They applied a Bayesian hierarchical linear analysis, and that accounted for industry effects, firm effects, and year effects. In the end, I should mention by now, Bayesian analyses have been developed for any kind of models you can think of, or so regression analysis, but also SEM, survival statistics, they all exist. They use, like everybody else these days, Markov chain Monte Carlo simulation. And in this case, they had large data set. They used flat uninformed priors. Here's what they found. So for these different decisions, and buying units is the top on the table there, they got probability of the effect that action actually improved performance. Performance for them was measured in financial accounting returns. And this is not a p-value. Keep in mind, if you have any question what the p-value really does, I strongly encourage you to read two recent editorials of the American Statistician by Wasserman and Lazar that outlines all the stuff that the p-value you may have thought is telling you, but it's not actually telling you. So this here is a probability statement of actually a positive financial return estimated based on your data. So there is an 81% chance of improving performance. But here, as I said, this is just, again, a dichotomous judgment. Your data tells you so much more. So that's why these posterior distributions are really important. And this graph also contains the information of the 81% probability, which is the area under the curve that is above zero. But it also tells you immediately, or you can convert that easily into effect sizes for the bottom line, and thereby the effect size in actual terms. You could use the dollar values or percentage increases or something that's meaningful. Plus, it does give you immediately the counter probability. So you can tell people there is a 90% chance that you actually might lose money. Again, p-values cannot tell you that. But there's a lot more in this graph than that. So it tells you about the mean. Even visually, you can kind of imagine where it is. It tells you about the range. How much can I possibly lose? What would be the max? It tells you if the tails, how thick the tails are. It could tell you that the functional form of a single peak distribution might be inaccurate. What if it's bimodal? Well, what if it's a lot of companies losing and a few companies are actually winning, and they're winning substantially? This all would be completely hidden in your p-value evaluation. And thickness of tails especially, outliers, again, Will Mitchell was mentioned earlier, that's one of his pet peeves too. Outliers are highly interesting. They often have stories to tell. If we eliminate them from the analysis, we're running the risk of, especially in entrepreneurial settings, of killing the ones that really make the difference, because everybody is in the blockbuster win business. If I remove the blockbusters from the movie industry, I don't have the movie industry anymore. So again, these distributions tell you a lot about your data, and you spend a lot of time to collect this data. And by using a p-value evaluation on it, you're throwing away tons of information that might potentially be interesting and important with regard to understanding your phenomenon. You're also not conveying any of that information to your readers. This simple posterior distribution communicates very powerfully a lot of stuff that's in your data. So strong encouragement, even if you're a frequentist, you should choose more graphs of predicted effects as they are in your data to communicate those distributions of effects that you have beyond your p-value evaluation. So, and then I did mention this comparison graph is a little small, but this is out of their actual paper. For these other decisions that they had, you can see that these distributions are quite different. Some are much more narrow, some are much more flat. And I think that allows you a much deeper interpretation of what are the implications of these different decisions with regard to organizational performance. And so in that sense, I think this discussion showed that Bayesian analysis is really all about both effect sizes and effect uncertainty, and kind of looking at them and trying to interpret them simultaneously. See, one of the limitations of the p-value frequentist approaches is that we look at distributions very briefly, and then we use the p-value to say, like, either there is an effect or not. And from there on, we're not dealing with uncertainty anymore. We've removed the uncertainty from our evaluations. And that's why we also have a lot of theories, but the theories often make no really, we have a lot of theories that says this factor matters. We have very few theories that said how much it matters. We have very few theories that actually outline, quantify how much it matters. So if you think of physics, you know Einstein's famous formula. This is a clear theory that makes clear predictions that you can say for any situation that you want to apply it to. In my field, I do a lot of organizational learning. We do have some segments where there is theory that is so quantified. So the learning curve theory has led to predictions of accumulated knowledge doubled, reduction in production cost by 20%. This is the kind of quantifying, predicting theories that would be very helpful to managers. But with our p-value evaluations, we're just getting stuck in the situation of just being able to say, like, it matters, but not discussing and evaluating how much it matters and what the uncertainty of those effects really are. So you know that effect size evaluations are getting much more attention. So you should also already be in a training mode where effect size is, I think, a no-brainer, needs to be part of your hypothesis discussion, should actually, I think, be the core of your evaluation if you have something, a pattern that is of interest and that is supportive of your hypothesized effects. But the uncertainty is equally important. And I think currently we're still more struggling on how to do that. So, you know, the SMJ suggestion that you have to report the actual p-value. You have to argue about cutoff rates. But I think that's just the starting point. And again, the p-value has very limited information. And it's better to have flexible p-value thresholds. But it doesn't inherently resolve the issue that you're judging probability for the data based on a no effect in the data, which you then throw out. And so when you, if you use your p-value right and you concluded that there is an effect in the actual population, the p-value itself has done its purpose. It becomes obsolete because your assumption for calculating it was that there is no effect in the population, and you've proven that to be wrong, and thereby it served your purpose, but just for that dichotomous judgment, for probability statements about the effect, you cannot use the p-value. So that's the point here, that we really need to deal with that uncertainty. We need to explicitly address it. And this is nothing new. So old people like old researchers, Jacob Cohen, John Tuckey, they've already emphasized this, and we've not followed the path that they laid out. And we need to kind of, what Tuckey says, we have to discuss, model, and breathe uncertainty. And Bayesian tools are very nice with regard to trying to allow us to do that, and in a very transparent way. So Bayesian graphs of posterior distributions are powerful tools to estimate and report both the effect size and the effect uncertainty. As I said, that Bayesian magic is a little bit more, and these are complex methods. There is some good news. There are some recent books that are really, I think, good with regard to introducing. So I'm just going to expose you to McElrath's book, which comes also with a online version, textbook, and lecture series, and models in, or examples in R. And if you are more interested in examples out of the management area, still Eugene Hahn's book from 2014. Even though his examples with regard to it, they become more outdated with regard to the applications in the models, because the software just has moved so quickly forward. And here's what the software has moved forward. With Stata 16, with SPSS, we now have Bayesian models in there. They didn't used to exist. So in the 90s, we actually had a Stata person in one of our workshops when they started to offer it in order to promote it. And I can make you run a Bayesian model right here. It is for Stata. It is so simple. So if you have your Stata code for a regression line, so regression and then dependent variable, then all the independent variable, all you have to do to run a standard Bayesian on it, you got to put in front of the regression Bayes and space. So Bravo, Alpha, Yankee, Echo, Sierra, dash, space, and then run your regression. And it will run you a absolutely standardized Bayesian regression. Don't read too much into that, because then the program will make a lot of decisions that you might want to rather do yourself. Like, it will have uninformed priors. Maybe you want to use something different. It will have burn-in rates, and you need to check if the burn-in rates were sufficient and some other things. But the pure execution has gotten really, really easy. And you can then find out how to change those other things in statements after your regression. So this is really a far cry from what Bayesian was, and a far cry from what it was before the 50s and 60s, before we got computers of that power, because then you could just not run Bayesian analysis, not with Markov chain simulation. So if you are, and a lot of you are probably, I know, are trained in R, then Stan is your choice too. There is now a very developed and freely available Bayesian algorithms by the top people in the Bayesian field, and they're available for free. So that might be even more attractive than Stata and SPSS, where you still have to have a university that pays the licensing fee for it. So all this encouragement with regard to experimenting with it, it's not rocket science. Good, future applications. So I think Bayesian analysis can actually be applied to virtually any research question, any statistical problem, any empirical context. And I think we should do it, because it will give us another perspective. It will tell us more about your data. And that, I think, is the starting point for all the other stuff, what we learn from it. And there is no reason to throw the data away, but rather investigate it in all the different, cut it in all the different slices and perspectives we can get out of it. Resonating with Pren's earlier comment, but doing so transparently. See, one big problem in p-values is best model reporting, which then it's not a deductive test anymore. The p-value is just invalidated by you running multiple models. But if the p-value doesn't tell us so much, I still would encourage you run multiple models, understand your data, so that you can make good statements about what's happening in it and what's not happening in it. Use prior distributions implies opportunities for building on prior research and better accumulation of knowledge across studies. We're always talking about replication, and we're just not very good at instigating that it actually happens. Bayesian kind of opens the door wide. It asks you for what has been done prior to it. And thereby, I think that's a great opportunity to be exploited and do in a systematic way. Many management scholars consider the execution of Bayesian analysis difficult, partly because of the Monte Carlo Markov chain simulations and the specification of priors. But as I pointed out, computer software has made this a lot easier. And the other thing, with large enough samples, priors don't play as much of a role. Plus, there is an entire literature developing with regard to how to develop priors systematically. I think at this stage, what's really needed is that more management scholars are willing to become familiar with Bayesian analysis and then try to experiment with that powerful paradigm. And then I'm foreseeing what has happened to other fields, that Bayesian analysis will become an established key methodology in management research. And again, I'm going to just add also a couple other sources, but there's a lot of Bayesian resources available to you, because some other fields, including medical sciences, the AI field, biology, have embraced Bayesian statistics to a much higher degree than we have at this stage. But we can easily piggyback on what they've already done.